Good morning, FNA virtual show attendees. Since this method of presenting a paper is new to me, you'll have to excuse me if this transition between slide to slide is not as fluid as it would be when presenting in person. As an introduction, my name is Tim Donofrio, and I am Vice President of Sales with Can-Eng Furnaces International. I've been involved in the industrial thermal processing and equipment side of things for over 30 years. 22 of which have been with Can-Eng, and I've spent the majority of my career providing unique concept thermal processing equipment solutions for manufacturers of automotive lightweighting components. The automotive and mobility market is in a state of flux, which puts greater demands on thermal processing service and equipment providers. This presentation will outline the mobility market lightweighting trends we see today, a focus on recent advancements in the use of aluminum components and product applications in vehicles, a review of thermal processes, both conventional and newly developed applications for these lightweighting components, the challenges associated with the new aluminum component thermal processing solutions, and in closing, a review of what's headed down the technology pipeline. What will the future challenges be for both processors and equipment builders in the future? Lightweighting trends for aluminum vehicle components. There should be no surprise that there's been a constant push to reduce the overall weight of vehicles as a means of reducing fuel consumption as well as the emissions. The Center for Climate and Energy Solution reports the transportation sector is the largest direct source of U.S. greenhouse gas emissions, surpassing the power sector in 2015. Cars and light-duty trucks, including pickups and SUVs, are responsible for about 59% of transportation emissions, while medium and heavy-duty vehicles, which include tractor-trailers, large pickup trucks, vans, delivery trucks, buses, etc., produce about 23% of the transportation emissions. In March 2020, the EPA and the National Highway Traffic Safety Administration issued new greenhouse gas emission standards and fuel economy standards for new passenger cars and light-duty trucks. The Safer, Affordable, Fuel-Efficient Vehicles, known as SAFE rule, requires automakers to improve fuel efficiencies 1.5% annually for model years 2021 through 2026. The SAFE rule is less stringent than the Obama-era rule it had placed. That rule would have required automakers to improve fuel efficiency 5% annually for model years 20 to 25, reaching 4.6 miles per gallon fuel efficiency by 2025, versus the current SAFE program, which requires 39.87 miles per gallon by 2025. The most significant trend in the mobility market is the increased number of electrified vehicles produced. The automobile industry has been a beacon for technological innovation and a guiding light in how people change the way they live. The time for change has come again, and some report that the levels of mobility change coming over the next 10 years are likely to exceed those of the previous 50 years. Key to these developments are four trends most easily remembered by the acronym ACEs: autonomous driving, connectivity, the electrification of vehicles, and shared mobility. With all good technologies, there comes a time when buying the alternative no longer makes sense. As an example, cell phones in the past, or even color TVs in the 1970s. Predicting the timing of these shifts is difficult, but when it happens, the whole world changes. It has become clear that the 2020s will be the decade of the electric car. According to the Bloomberg New Energy Finance, battery prices fell significantly and are on path to make unsubsidized electric vehicles as affordable as their internal combustion engine counterparts in the near future. This will start the mass market liftoff for electric cars, which is predicted around 2022. Furthermore, by 2040, long-range electric cars will cost less than $22,000 in today's dollars, according to these projections, where 35% of the new cars worldwide will be plug-in. As vehicle manufacturers today push the envelope of lightweighting technologies, so do they impart opportunities for the development of new products, materials, manufacturing methods, and new thermal processing technologies. According to vehicle designers, 10% reduction in vehicle mass equates to approximately 6 to 8% reduction in vehicle energy requirements, which does promote enhanced electric vehicle range capability. However, downsizing has its limits, which is leading developers to seek out new alternatives or new approaches to managing these new components. Vehicle body component accounts for approximately 1/3 of vehicle mass, which includes body and white components. Advancements in lighter weight body structures through the use of ultra high strength steels, carbon fibers, aluminum, magnesium, and new joining technologies are all being used today as a means of reducing automobile mass. In an era of lightweighting technology advancement, we see a common trend where steel components are being replaced with lighter weight aluminum components. We see automotive manufacturers expanding the use of lightweight technologies and exploiting the use of aluminum materials in high volume vehicle assemblies. Traditionally, we have seen aluminum being incorporated into various forms and configurations such as powertrain castings and suspensions, as well as sheet and extruded shapes for the body, externals, and bumper structures. But today we see lightweighting materials being incorporated into high-volume automotive platforms in the form of thin-walled structural node castings or body structure extrusion stampings. Examples of this can be seen in the release of the F-150 truck platform conversion to aluminum. Through the integration of lightweight aluminum panel and structures, engineers yielded benefits in smaller powertrains to drive the vehicle, reduced suspension burden, and less elaborate structures. By 2020, net aluminum demand is expected to increase to 570 pounds per vehicle, due to the increases for all vehicles utilizing aluminum enclosures, body and white, and chassis components. These demands are a result of manufacturers' desire to meet long-range greenhouse gas emissions goals, as well as satisfying the ramp-up of electrified powertrain and battery electric vehicle platforms, which use greater amounts of aluminum sheet, extrusions, and castings for weight savings to achieve the range targets. It is also reported that body enclosure components will make up the largest growth potential moving forward. Vehicle manufacturers today integrate aluminum components in considerable applications that include closures, body and white, chassis, powertrain, driveline, transmission, heat management, braking systems, steering, wheels, and trim, some of which are covered in the images shown in this slide. This presentation will focus on new thin-walled casting components used in vehicles today as part of structural and crash management system components, body and white, chassis, and electric vehicle components such as battery cases. Aluminum has been a highly recommended source material for castings by vehicle engineers for lightweighting applications, largely due to unique strength, weight, and corrosion properties. Furthermore, casting properties can be enhanced through novel casting methods such as vacuum high-pressure die casting and post-casting thermal treatment processes, which can be tailored to provide the engineer with a lighter, cost-effective alternative possessing strength and ductility performance levels that are comparable to previously developed steel stampings and/or multi-component fabricated assemblies. The implementation of newly developed aluminum components into automobiles does come with its challenges, which will need to be overcome in order to be successfully implemented. This paper examines the following: challenges developing a non-traditional thermal heat treatment processes for new aluminum castings developed to replace previous high-strength steel family of fabricated stampings, traditional thermal processing options available to manufacturers of body components, and the challenges associated with developing new heat treatment processes, overview of newly developed thermal processing system concepts which can achieve property and physical requirements, focus on new quenching technologies for aluminum castings, and how new heat treatment processes can be integrated into high volume vehicle manufacturing processes. The following slide represents a conventional batch type thermal processing system. In this system, parts are generally loaded into fixtures, trays, or racks and delivered to the heat treatment system by an operator, typically via a fork truck. These loads, or charges as thermal processors call them, are then individually heated and, depending on the material's alloy and property requirements, are held at temperature for various times, allowing the alloy to homogenize and then potentially discharge rapidly to a quench system. Again, depending on the properties will dictate the thermal process required. This method is acceptable for small capacities or for thermal processors that require a high degree of process parameter flexibility, where they need to change time, temperature, and quenching methods between individual batches on a regular basis. However, it must be known that this is the least efficient system for high volume processing. The following heat treatment system represents a conventional T6 type thermal processing system. In this system, parts are loaded into fixtures, trays, or racks and delivered to the heat treatment system. These loads or charges enter the system and traverse or convey through the various solution heating and soaking zones, subsequently through a quenching stage, and finish through post-quench artificial aging, heating, and soaking zones until they are finally discharged at the opposite end of the system. This particular layout shows an inline concept. However, these systems can be arranged in a multitude of configurations. They can be arranged in a U-shaped layout or even an over-under configuration where the solution furnace is positioned above the aging furnace. Conventional conveyance systems include roller hearth, walking beam, conveyor belt, pusher, and overhead rail transfer systems as a means of conveying baskets, charges, loads through the solution, quench, and age portions of an aluminum heat treatment process. Conventional linear conveyorized T7 systems consume considerable floor space, and when integrated with the quench system are significant in size and energy demand to provide the quenching capability for large mass baskets or racks. Facility infrastructure requirements are large as well as the work in process inventory requirements to keep the system fed and backed up continuously. Energy consumption is quite significant for long linear conventional T7, T6 systems, mainly due to their large external surface area conduction losses and additional conveyor roll conduction losses and door opening losses as a result of large baskets and trays. In addition, conveyance systems can be complicated and costly to maintain over time, as they involve many internal moving parts and are subject to thermal stresses and integrate considerable lengths of drivetrain and drive units that constantly require attention and maintenance. Thin-walled, high-integrity casting product can be at a disadvantage as a result of heating and quenching large racks with a large number of castings loaded into it through a conventional system. This is a result of large, dense loading of baskets and the challenges in developing uniform heating and holding of temperatures for the critical T7 process. Furthermore, the most important step in the process, which involves air quenching, can be greatly compromised by these challenges in rapidly conveying a large rack from the discharge of the solution to the quench station in the required time, and in addition, the uniform and wrapping quenching can be compromised by the lack of developed quench flow through the rack due to the size of the rack and or density of loading of that rack. In collaboration with the industry and in determining the needs of the manufacturers and processors, it was clear that they were looking for support in meeting the demands of their customers and satisfying the quality and cost pressures put upon them. Their main concerns regarding a new efficient heat treatment system for thin-walled structural components included that the system provided efficient and flexible geometry processing capability. Essentially, the system must be flexible in terms of processing parameters, as well as processing type of part and the geometry that could be processed. Furthermore, manufacturers were looking for a system that essentially reduced their work in process inventories between operations. Essentially, a system that's capable of being closely coupled with the upstream and downstream processes, thereby minimizing the amount of inventories required between operations. A high level of importance was placed also upon ensuring the system provided best technology available for part dimensional accuracy, essentially utilizing in-house know-how and experience in preventing or minimize part distortion as a result of the thermal process, which could minimize or eliminate the need for post-heat treatment processes, especially important for large components such as battery cases where their corresponding component mating surfaces need to accurately fit. The system must be of high capacity, high efficiency, and provide a uniform precision air quenching technology. The system must be of a simple design and provide ease of maintenance. Product traceability and data collection is considered a need of these systems as well. Today, there are new, more efficient thermal treatment options available to manufacturers and processors of high-integrity, thin-walled structural vehicle castings. Through the development engineering of an existing rotary hearth technology, including robotic handling and precision air quenching technology, there are now options available that eliminate the challenges and inefficiencies plagued by operating a long linear T7 structural casting heat treatment system. In recent applications engineering review, both the linear conveying system was evaluated alongside with the rotary hearth conveying system for space analysis. When laying out both systems of equal capacity, the rotary hearth concept is clearly more space efficient, requiring 35% less space than the continuous roller hearth linear conveying system. Furthermore, when comparing the system's overall conduction energy losses, the rotary hearth system provided greater efficiency over the linear roller hearth design as a function of space benefits. These newly configured heat treatment systems offer processors both captive and commercial benefits over conventional methods when processing newly developed lightweight aluminum vehicle components. The rotary hearth heat treatment system described in this presentation just demonstrates an example of newly developed methods for processing lightweight aluminum vehicle components that improve quality and productivity while also reduce the cost pressures which processors are under. These benefits include more compact design, less floor space required compared to conventional processors, reduced fixturing and racking mass requirements as a result of processing smaller batches, reduced cycle times associated with a more efficient heat up of smaller batches, more efficient smaller quench systems that require less floor space, infrastructure, or facility burden requirements, as well as lower horsepower requirements. Through the integration of robotic automation, minimal heat treat operator requirements, through the integration with upstream and downstream processes, these systems do reduce work in process inventories and are considered true lean manufacturing cells. Reduced energy consumption and emission potential, improved quality benefits, reduced product variation as a result of smaller lots for more uniform heating and quenching. The processors realize improved uniform properties as well as more uniform quench, which reduces the opportunity for part-to-part distortion. Through the integration of robots, automatic part serialization, identification, and critical part processing, parameter tracking, and data can be collected. These are a number of benefits that can be realized by processors. What is in the future for manufacturers of lightweight vehicle component providers? Well, I certainly do not have a crystal ball. However, certainly aluminum content in vehicles will continue to increase to support the new vehicles of the future. As an example, battery electric vehicles, further weight reductions will need to be explored to offset the conflicting interest between battery weight and vehicle range capability. I'd like to thank you for your interest in this presentation, and I would encourage you to reach out to me individually at the following email address, or you can find more information regarding Can-Eng at www.can-eng.com, where you can learn more about Can-Eng furnace designs that have served commercial and captive heat treaters, stamping and fastener companies, automotive component producers, iron and steel industries, aluminum foundries, agricultural, construction, and appliance manufacturers for almost 60 years. Can-Eng has gained an international reputation for design innovation, quality workmanship, and dedication to service. Thank you.